Okay, so I'm covering rational exponents. This is basically, rational exponents are like the precursor to radicals, because radicals, square roots, and all that can be written as rational exponents. You don't really work with rational exponents a lot. Most of the time we work out with them in square roots and cube roots and in that form, not as exponent form. But understanding how to work with them in exponent form might make it easier for you to understand radicals in general. So I'm hoping that this will help you understand like sort of what it means and what it does. And so that way when you go to the radicals, which, you know, this comes next here, that it will sort of make sense. So what are rational exponents? So the word rational in math basically means that it's a fraction. So, you know, it has a different meaning depending on if it's math or not. So rational exponents are just exponents that have fractions. So we haven't really dealt with any of those before. We've been basically just having whole number and negative exponents. So all the rules of exponents work with rational exponents. So they work even if they're fractions. So you don't have to learn any new rules. You're just applying these rules to fractions instead. So having a calculator that can do fractions can make your life a whole lot easier. Whether it's a physical calculator that can do fractions, or if you use the Decimal Scientific calculator that does fractions, that will save you time, and then you won't be making mistakes with the fractions. Because I'd rather have you be able to do the rules than to spend all your time trying to figure out the fractions. So, like I said, rational exponents connect to radicals. So, basically, if you have something that's to like a 1/2 power, that's the same thing as a square root. So that's this rule. Oops, make sure I actually get to my pen. That's basically this rule right here. So if you see something to the 1/2, that is equal to the square root. And so if you have something that's to the 1/3 power, that is equal to a cubed root. So that's like the definition of a square root and cube root. That's how they're defined. But we can also have rational exponents that are not just one on top of the fraction. We can have other numbers, and you can write those either way. Basically, you can either put the top part of the fraction on the inside, or you can put it on the outside. So which way you do it usually determines, you can get the same answer either way. I pick which one I use based off of what seems easier. I usually find it easier to kind of try to make it as simple as possible. So I tend to put it on the outside, the one on the right where the m is outside the parentheses, but you can put it on the inside, either one. So an example of this would be like if I had a to the 3/2 power, I can either rewrite that as a cubed and then to the square root because of the 1/2. So actually, to make this a little bit easier, you can think of this as a to the 1/2 power to the 3rd power. So 3/2 is 1/2 times 3. So that's where that 1/2, where the square root comes from. So you can think of this as a cubed to the square root, or you can take the square root of a and then cubed it. So the bottom is basically telling you what root it is, whether it's a square root, which the denominator would be 2, cubed root, the denominator would be 3, 4th root, denominator would be 4. So that bottom number is telling you what the root is. So n here is the root, and then the top number is what's telling you what the exponent is going to be. And then you can choose which way to write it based off of what makes sense to you. So again, with square roots, the square root is the same as a 1/2 power. So sometimes, and this makes things easier on your calculator, like maybe your square root button, you can't find it, but you have your exponent button, you can use the exponent button instead. Just make sure that you put parentheses around it. So if you wanted to do the exponent version, you need to put parentheses around the 1/2. Otherwise, it will do n to the first power and then divide the answer by 2. So if you choose to use like the 1/2 exponent instead of the square root button, you just need to make sure that you put parentheses around it. I tend to use the rational expression, the rational exponent version, the fraction, when it's like a 4th root or a 5th root or something higher, because my calculator, it has, or even a cubed root, like my calculator has a square root button, but not every calculator has buttons for other roots. And so if your calculator doesn't have a button for those other ones, it's often easier to write it as a fraction and use your exponent button instead. So that's just something that you can, use on your calculator either way. If, I have to hit another button to get to the square root, but I don't for the exponent. So, depending on how fast you want to be, you might want to decide to do the exponent. But you do want to be able to convert from one form to the other, because sometimes one form is easier to work with than the other. And so being able to go from one to the other and back and forth can really be beneficial to you. So basically, I'm just going to go through tons of different examples of how we can simplify these things, rewrite them, just so you can get used to that, and then we can start working with the rules of exponents and how those all work. So here we're going to simplify, and so simplify, you're basically evaluating it, trying to find the answer. And so 36 to the 1/2. So if we think of that 1/2 exponent as the square root, this is just asking us to take the square root of 36. And so the square root of 36 is 6. So even though it's in a different form and you have this 1/2 exponent, if you know what that means, you can get the answer even with your head, because you know what the square root means. You don't really need a calculator, but you could verify that in your calculator. The negative 36 to the 1/2 power. So here it's easier to put it in a square root form, and you can think, okay, I'm taking the square root of a negative number, which is going to give us a complex number. And so we've done complex numbers, right? We try to remember. Having that week off has kind of thrown me off with what we've talked about and what we did it, because I took vacation. I just want to make sure we've talked about complex numbers before. Oh yes, we definitely did. Okay, so this is going to give us an I because we have the square root of a negative, and so we can pull out that I. And then you're taking the square root of 36. And then the square root of 36 is 6. So we usually just put that in front, and so it's this 6i. So, or you can say that it's not a real number because it's an imaginary number. But understanding that the rational exponent is a square root can help you look at this and say, okay, I'm actually going to get an imaginary number out. So that can help you if you can, kind of go through and convert from one form to the other. The next one here, we have negative 36 to the 1/2 power. And so when that negative is not in parentheses, it's not included with the exponent. So the negative is outside of the square root in this case, if we're converting it. So the square root of 36 is 6. So this gives us negative 6. So it's important to really understand where the negative is placed, where the parenthesis is placed, because that changes your answer. You can see here it changes it from 6 to 6i to negative 6. But the key for doing all of these is it's helpful to convert it to a square root symbol, just because we know how to do that. You know, like we can think about those in our head. Thinking of it as a 1/2 is a little harder to kind of do in your head. It's not natural. I mean, we're not taught how to do 1/2 powers when we're growing up, but we're taught how to do square roots. Are there any questions? Okay. So next one here, again, we're simplifying. These are now 1/3 powers. So the 1/3 is a cubed root. So I've got, I can get, why is it not trying to get my pen right here. So 125 to the 1/3 power is the same as the cubed root of 125. I don't think you guys really have memorized what the cubed root is of 125. Most people haven't. When you have things that are 1/3 powers like this, or 1/4 or 1/5, sometimes it's actually easier to leave it in the fraction form. And the reason why is if instead of writing it as the cubed root, we can rewrite the 125 as an exponent, and we want to write it in some number, you know, whatever its exponent form is. So 125, if I did a factor tree to do the prime factorization, that is 25 times 5, and then 25 is 5 times 5. So 125 would be 5 cubed because I have 3 5s here. So I could write it as 5 cubed, the 125, and then have the 1/3 power out there. And then you can use your rules of exponents, where if you have an exponent on another exponent, you multiply those together. 3 times 1/3 is equal to 1, and so we just get 5. Which is the same thing as taking the cubed root of 125. But in this case, I think taking the cubed root of 125 and trying to do it with a radical is less intuitive for people. But if they convert it to a rational expression and then follow the rules of or rational exponent and then follow the rules of exponents, you can see why a cubed root cancels out the 3. Because 3 times 1/3 is 1, and so that's why those cancel out. So we can do the same thing here. We have a negative 125 to the 1/3 power. So this would be a negative 5/3 to the 1/3 power. So the thing about negatives, though, is that you always have to determine if you're going to get an imaginary number first, and then deal with multiplying those exponents together. So like I can't just do negative 3 to the 1/3 first. I have to first determine, am I going to have a complex number? And that's with square roots. So we have a cubed root because it's a 1/3, so we don't need to worry about that. And with roots like this, 1/3 or 3, if the denominator is odd, you can have negatives basically in there. If the denominator is even, that's where you have to think about having complex numbers or not a real number. So it's the same with the rules of exponents. If it's a even root, you have to worry about negatives. If it's odd root, you don't. So because the denominator is odd, I don't have to worry about a negative, and what that means is that my number is going to be negative. So I'm going to basically have a negative, and then I can multiply the 3 times the 1/3, which is 1. So I'm going to get a negative 5 here. And this is actually going to give me the same answer as negative 125 to the 1/3 power. So I basically have a negative and then 5 to the 5 cubed to the 1/3. And it's 5 cubed because 125 is 5 cubed. And then that would also give me negative 5. So those are just some examples of exponents like 1/3. And let me just write here, odd denominator. Let's say negative in means negative out, if that helps. So negative like inside the 1/3, you're going to get a negative out as your answer. So that's the kind of rule when you have an odd denominator here. Are there any questions? Okay, so we've looked at square roots, we've looked at cube roots. So now let's look at things that are different, that we don't generally write as radicals. So now we have other fractions as exponents. So here I've got 3/4. And again, I'm doing a positive and then a negative in parentheses and a negative, so you can see how these work. So I recommend for things like 81 is to write it as, any of these numbers when you're dealing with these things, write it as their prime factorization. So I'll do the factor tree up here. 81 is 9 times 9, which is 3 times 3. So 81 is 3 to the 4th power if you're doing the prime factorization, because we've got 4 3s multiplied together. So I find that helpful when I'm working with these. So I'm going to rewrite 81 as 3 to the 4th. And then I've got my rational exponent. So we can use our rules of exponents here to multiply those together. 4 times 3/4. So when you multiply a whole number by a fraction, you're multiplying the tops together. So 4 times 3 is 12. So that's 12 over 4. And then 12 divided by 4 is 3. So this is the same thing as 3 to the 3rd power. And then 3 to the 3rd power, if you do that on your calculator, gives you 27. So this is one way that you can work with rational exponents, and you don't have to convert it to like a square, 4th root, or convert it to a radical at all. You can deal with only the exponents, and as long as you can do math with fractions or have a calculator that can do that, you can simplify it without ever having to convert it to something else. Now the one in the middle, we have a negative 81 to the 3/4. So that would be negative 3 to the 4th to the 3/4 power. So here's where we have some issues, because we have a negative and then our denominator is even. So I talked about this here with an odd or even denominator. So with an odd, it doesn't matter if you have a negative in there. But if you have an even denominator, if the denominator is 2, you're going to get an imaginary number. But if it's anything larger than 2, like 4, we don't have, our imaginary numbers are only with square roots. We have a 4th root here, because that 3/4 means a 4th root. So let me write that here. So, and this is an even denominator. And even denominators cannot have negatives in there. So if you have a negative number to an even denominator for your rational exponent, basically, you can't get an answer. You're going to get you're going to get an error if you put it on your calculator, especially because it's not a square root, it's a fourth root. So even denominator, if you have a negative in, not a real number out, you can't find an answer for that. So just a little basic rule there. So if we have a negative 3 to the fourth, and then that's inside something, we have a rational exponent with a denominator of 4, we're not going to get an answer. So we're going to say it's not a real number. And it's not an imaginary number either, because it's not a square root. It's a fourth root because of the 4 there. Now, on the right, this is different, because if you have that negative and there's no parentheses, you can assume the parentheses are only around the number 81. So that negative is not included. So now we're taking the fourth root of something that's positive, which we can do. So we rewrite 81 as 3 to the fourth. And then we have the 3/4 outside there. And so now we're going to do something similar to what we did with the first example here, where you're going to multiply those exponents. 4 times 3/4. And when you do that, you're just going to end up with 3 to the third, because the 4 and then the denominator of 4, they cancel out. So 3 to the third is 27, so we get negative 27 here. I know this is probably rational exponents are a little tricky, because there's a lot of rules that you have to think about with this even denominator, odd denominator thing. Do you guys have any questions so far? Okay. Here I'm again working with the 81 there, and same with the 3/4. But now we have negative exponents and negative fractions. So I want to show you how that works when you've got your negative exponent going on. So I'm going to start on the left here. 81 is negative 3/4. So that negative exponent, our rule with the negative exponent is that we can make it positive by taking the reciprocal. So this is the same thing as 1 over 81 and then to the 3/4 power. So you take the reciprocal of what the base is, and then the exponent becomes positive. So we have 1 over 81 to the 3/4. So now I'm going to use the fact that 81 is 3 to the 4th power. So we have 1 over 3 to the 4th. And then we have 3/4 as our outside exponent. So our rules of exponents, when you have something like this, is that the outside exponent goes to the top and the bottom of the fraction. So we basically have 1 to the 3/4 over 3/4, or 3 to the 4th over 3/4. I should have used different numbers there. It's getting difficult to say this. So 1 to any exponent is always equal to 1, even if it's a fraction. So 1 to the n being any number, so I'm going to just say a real number, that's equal to 1. So it doesn't matter that I have a fraction as my exponent on 1, it's still going to be equal to 1. Now that denominator again, that 4 times 3/4, that cancels, that gives us 3 to the third. So 3 to the third is 27. So in this case, we end up with 1 over 27. So you could think of this as 81 to the 3/4, which we did on the previous slide, and then we're taking a -1 exponent there because the rules of exponents say that 3/4 times -1 is -3/4. So you can find out what 81 to the 3/4 is, which we did on the previous slide, and then take the reciprocal of it because of the -1 power. Middle example here, again, we have the -81, and then it's to the -3/4 power. So because the denominator is even, the denominator on the 4, we've got an even number right there, and then we've got a negative inside the parentheses there. That combination means that it is not a real number. That is the same combination that we had on the previous slide. It doesn't matter whether it's a positive or negative exponent there. What matters is what is the denominator. And if it's even denominator with a negative inside the parentheses there, it is not a real number. So now example on the right, we have -81 to the -3/4 power. So I can think of this as -81 to the -3/4, because that negative is not part of the exponent because it's not in parentheses. So we already found what 81 to the -3/4 was, because that's what we have on the left here. So this will be with -1 over 27. So I'm just using my previous work here to kind of do a shortcut. But the basic thing is, when you're dealing with these rational exponents, is to follow your rules of exponents. So that's what we did. We took that negative exponent, we made it positive by taking the reciprocal. We rewrote our number as a power of primes. We used the fact that you distribute, you multiply those exponents together. So even though they have fractions, you're still following the rules of exponents. And that can make it easier when you're simplifying these things. If there are any questions?
Stephanie, I have a question.
Yeah.
So on the first one, when you took 1 3/4 over 3 to the 4th power, 3, and then exponent was 3/4, how did you get as a denominator 3 to the 3rd power?
So that, I actually showed that here. The first example on the left here, 3 to the 4th.
Oh, gotcha.
Times 3/4. Yeah. So
okay.
I was just doing a shortcut because we had done that previously.
Right.
I just didn't show that stuff. Yeah. That's why I actually used the same numbers here, so that we could do some shortcuts and I didn't have to show the same steps every time. Are there other questions? Okay. So again, most of the time, and you guys are not going to see this stuff all that often with the rational exponents. The reason why we're going over it is just because you will see things with radicals, with square roots and cubed roots, and that way you kind of understand how to work with those types of exponents so that if you wanted to convert it to one way or the other, you can. But most of the time, you're not really working with these types of exponents, not unless you're going to calculus. And We do have people that have to go on to calculus and they're going to have to work with this, but most people don't have to go on to calculus. And so this is just, it's the reason why you're learning this. Well, the people are learning for calculus, but the rest of you, it's more of a way to get your brain thinking about how you can convert things into other, just a way to see something and then try to think about it and see it in a different light. Like, this is what I see, but can I rewrite this differently? How else can I, it's like you're looking at a problem and then you're like, well, I can't figure out a solution, but let me try to look at it from a different angle. That's sort of what you're learning here, is trying to look at something from different angles to see if there's a way that will make it easier. So now let's throw in our variables. And once you have variables, you can't actually figure out what the answer is because it's a variable. You don't know what number the variable is, so you can only simplify it. And so that's where really being able to convert from one form to the other is really helpful. So from here, we just want to write the expressions using radical notation. So that means you're converting these fractions into something with like square roots, cubed roots, and so on. Assume that all variables represent positive real numbers. So I've got z to the 3/10 power. So this is where we're going to use, let me find it, the bottom rule here, a to the m over n equals, and then you can choose which of the two ways to write it, whether you have your exponent on the inside or the outside. Both are equivalent. So for z cubed over 10, I'm reading it the way, z to the 3/10 power. I actually, when I'm just rewriting and I'm not trying to simplify, I will actually do the z cubed and then do the 10th root. So if I'm not trying to simplify, I will convert it this way. It's where I'm trying to simplify that I will write it differently. So on the top is basically the exponent. So what I just naturally do is I put the exponent on the z, and then I take that over 10 to give me the 10th root. So I draw my square root symbol, and then I put the 10 up there indicating that it's a radical, it's the 10th root. And we can't simplify that. If the number inside the root is larger than the root of the number outside, so if instead of 3 I had like 15, I could simplify this. But if it's smaller, we can't simplify it, so it just stays as it is. Now, in the middle here, I have 8 times z to the 3/10. So that 8 is not part of the exponent because it's not in parentheses. So the 8 will stay in front, and then you're basically converting z to the 3/10. So since I already did that on the left, I can write this as 8 times the 10th root of z cubed. Now, on the right, the 8 is in parentheses with the z. So that means when I convert this, the 8 and the z are getting the 3rd power. And then it's to the 10th root. So you can see that I'm basically taking this part, and then I'm taking that divided by 10 in the exponent to write it as the root. And then when we simplify this, we would distribute, so we'd have 8 to the 3rd power times z to the 3rd power. So we want to try to simplify further, and we could rewrite 8 as as its prime factorization. 8 is actually equal to 2 to the 3rd power. So we have 2 to the third power, 2 to the third, and then z to the third. I know there are 3's all over here. And my 2 looks like a z, so I want to be very careful, like make that look like a 2. Our rules of exponents say we multiply those. So 3 times 3 is 9. So when we finally get our simplified version, we end up with 2 to the 9th and z to the cubed inside there, and then we have the 10th root. Are there any questions? Okay. Now we're going to go the other way around so that you can get practice there. We're going to take these, the radicals, and we're going to convert them back into fractional exponents. So I have the 7th root of z to the 4th. So first thing I do is I turn the root into its frac form. So the 7th root is equal to the 1/7 power. So I do that first. And then I multiply my exponents together. So 4 times 1/7. And that gives you 4/7. So this is equal to z to the 4/7. In the middle, I have the cubed root of 8x. So I'm going to have 8x, and then I'm converting the cubed root to a 1/3 power. And we could just leave it like that, but we should try to simplify. So 8 is written as 2 cubed. So we have 2 cubed, and then x, and then the 1/3 power. And we can simplify this. So we can use our rules of exponents where you distribute basically that outside exponent to the inside. So I have 2 to the 3rd to the 1/3 power, and then x to the 1/3 power. And then 3 times 1/3 is equal to 1. So I just have 2x to the 1/3. So I've rewritten it using rational exponents, and then I went further and I went to simplify it so that I can get it into basically lower terms or smaller numbers. Now on the right, we have 11 and then the square root of t. So that's 11, and then t is the only thing that gets the exponent because that's the only thing that's in the square root, and the square root is equal to a 1/2 exponent. So this is equal to 11 times t to the 1/2. Any questions? Okay. 2 more here. I have x to the 2/3, and I want to put this back into a radical. So I take that x, and then I take my exponent, x squared. I read that exactly as I see. And then I see that divided by 3, which is telling me that it's going to be the cubed root, or I could say that's the 1/3 power if you want to write it that way instead. But this is going to be x squared, and then you can write it as the cubed root of x squared. And when you're entering these into ALEKS, there is a button specifically for different roots, so make sure you click the right button so that you can put these in correctly. Now the one on the right here, 6r to the negative 2/5. So we want to write this with a radical. So first off, the 6 is not part of this. So this is 6. And then we have, I'll put in parentheses, r to the negative 2/5. So if I'm going to write it the way that I've been doing, you can have r to the negative 2 power, and then the 5th root of that. Now, in this case, this is kind of a weird way to write these. So going back to the initial, I'll write the rule here, a to the m over n. So far, I've been writing it as a to the m to the nth root. But the other way to do it is to do the nth root of a and then the m on the outside. And when I have negatives as my exponents here and I'm trying to put them in a radical notation, I actually find that the second version there is a little bit easier for me. So I'm actually going to use the second version where this is the 5th root of r and then put the negative 2 exponent on the outside, because it's a little easier to work with that than what happens when you have that negative 2 on the inside. So that negative exponent, that means you take the reciprocal. So that's going to become 1 over the 5th root of n, and then squared, and then I've got that 6 in front. And that 2, basically, you can apply that to the top and the bottom. So that outside exponent gets applied to the top. 1 squared is still 1. And then to the bottom. And so this allows me to write this as a single fraction with 6 on top. I have my 5th, oops, I wrote n instead of r. R. And then the exponent of 2 right there. So, because 1 squared is 2, 1 squared is 1, and then I have 6 times that. So that's how I got 6 on top. So I find that writing it this way, when I have negative exponents, I tend to use this form. Otherwise, I may use the other form, depending on how I want to rewrite it. You want to be able to be flexible about which form you use, converting from one form to the other, because that really gets you to see, well, what's another way that I can write this? How else can I look at this? Is one way easier than the other? And that's a real good skill just for problem solving in general, even if you're never going to be doing this ever again. There. Any questions so far? Okay, so just to review, we have all of these rules of exponents, and this just came directly from the textbook. And they're the same rules whether you have fractions as your exponents or not. And so there's examples showing that, where if you're multiplying two things together, you add their exponents. The tricky part with fractions means that you need to have a common denominator to add them. Same thing when you're dividing things with exponents, you subtract the exponents. You need to have a common denominator. We've got the rule where you multiply your exponents together. So the rules are all the same. They just get a little trickier when you have fractions. So you know, I've been basically kind of walking you through some of the simpler ones. Now we're going to get into the more complicated ones here. And we're going to work with just the exponents, the fractional exponents here. So we're going to simplify these using the rules of exponents. We're going to leave them as having fractional exponents. So I'm starting with simple. These have a common denominator. That's going to make our life really easy. So we have 2 to the 2/3 times 2 to the negative 3/3. When you're multiplying things with exponents, you add the exponents. So we are going to have 2, and then we add the exponents, 2/3 plus negative 5/3. So that's my exponent. I just kind of read it like that. It's a lot easier when you have whole numbers. When you have fractions, it starts to look a little messy. This is where having a calculator that does fractions can make things easy for you, because then you can just use the calculator to do it rather than trying to get a common denominator. But we have a common denominator here, so we can just add them. 2 plus negative 5. So you're adding the tops, which is the same as 2 minus 5. So that gives us a negative 3. So this is equal to negative 2 to the negative 3/3 exponent. Now, negative 3/3, I can reduce that. That's equal to negative 1. So this is equal to 2 to the negative 1 exponent. And then that negative exponent means you take the reciprocal, and that would be 1/2 to the 1, or just 1/2. So this problem simplifies to 1/2. Now the example on the right, we subtract exponents when they're on a fraction like this. So I'm going to have q, and then 5/4 minus 1/4. So top minus bottom. These have a common denominator, so that means I can subtract them immediately. 5 minus 1 is 4. So we get q to the 4/4. Then 4/4 is 1, so we're just left with q. So in both of these examples, the fraction actually disappeared when you went to simplify these. Are there any questions?
I have a quick question.
Yeah.
I'm Tamika. On the first one, you don't multiply the 2's by each other?
No.
Okay.
So yeah, when you have exponents, it's really tricky when you see them with fractions, because when you look at it, you want to multiply the 2's, but you don't, because you're doing stuff with the exponents only.
Okay.
So the base stays the same. If it's easier to think about it or to look at it, you can think of this as maybe x to the 2/3 and then x to the negative 5/3. You're not going to multiply x by x because that doesn't really do anything. You know, it's like you're not inclined to multiply those together. I think it's with the numbers that it gets confusing. But you're multiplying it. This is basically the same thing as if I was doing x squared times x to the negative 5th, where you add the exponents, but we've just got fractions involved. So the base stays the same. It just looks more confusing because you've got more moving pieces. Does that help?
Yes.
Okay. Are there other questions? Okay. So again, we're just practicing our rules of exponents here. That's all we're doing. So on the left here, I've already kind of shown that some of this where you multiply your exponents together here, and it works the same if you have a fraction. So we've got x to the 1/2 times 8. And so you multiply the top of the fraction by the whole number, and that gives us 8/2. And then you can reduce, you can divide that out. 8 divided by 2 is 4. So this gives us x to the 4th. Now on the right, I've got this exponent of 3, and I need to distribute it to everything in the exponent here. So it's helpful to rewrite them all separately. So we've got 2 gets the exponent of 3 on the outside. Then I have x to the 2/3, which gets the exponent of 3 on the outside. And then y squared gets the exponent of 3 on the outside. And now you multiply exponents together, and we can do 2 to the 3rd power. 2 to the 3rd power is 8, so I can write that as 8. Then I've got 2/3 times 3, so I can write that as 6/3. And then for the y, 2 times 3 is 6. And then I can reduce or divide 6/3. 6 divided by 3 is 2, so I got 8x squared y to the 6th. Are there any questions? Okay, getting more complicated. We're throwing in some negatives here. I've got m to the negative 1/4 over n to the negative 1/2, and then to a negative 4th power. Whenever I have things with negatives, if I've got a negative on the outside and negatives on the inside, I will distribute my exponent first, because that's going to allow me to cancel out the negatives, and then I don't have to do any reciprocal stuff at all. So the exponent on the outside gets applied to the inside. So I'm going to have m to the negative 1/4 get the power of negative 1/4. And then n to the negative 1/2 gets the power of negative 4. And we multiply those together. So negative 1/4 times negative 4 will give us a positive 4 over 4. Might be easier if I just write this to the right here. And then the denominator, negative 1/2 times negative 4, will give us a positive 4 over 2. And then you simplify those exponents. 4 divided by 4 is 1, so that's m. And then 4 divided by 2 is 2, so that gives us n squared. And I didn't have to do any reciprocal stuff with the fractions because I knew that multiplying those together would cancel out the negatives, and then I didn't have to deal with that. Now on the right here, I have a whole bunch of stuff going on, and I'm going to just distribute my exponents, and I'm going to be very careful so that 4 distributes to the negative 1/3. And I just always save my reciprocal stuff to last. Then the b to the 1/2 gets that exponent. Now the 10 is going to the next part, so I have a to the negative 1/2, the 10, and then the b to the 3/5 has the exponent of 10. Now I'm going to multiply all of my exponents. So on a, I get negative 1/3 times 4, so that's negative 4/3. b, 1/2 times 4 is 4/2. I get another a, negative 1/2 times 10 is negative 10/2. And then b, 3/5 times 10 will give me 30 over 5. So now I'm going to try to reduce all of those exponents here. Negative 4/3 does not reduce. But on my B, 4 divided by 2 is 2. On A, negative 10 divided by 2 is negative 5. On B, 30 divided by 5 is 6. Now I'm going to rearrange them so that I have the A's together and the B's together. And I'm going to just put those in parentheses so that you can kind of group those together. And now when you're multiplying, you add exponents. And so our negative 4/3 and negative 5, we need to get a common denominator there, or this is where using a calculator would be very handy. So we're basically doing negative 4/3 plus a negative 5, which is a negative 5/1. And that's to simplify the A. So I'm going to do this by hand just to show you. So I got to get a common denominator. So I multiply the top and the bottom by 3. And negative 5 times 3, that will be negative 15. And then 1 times 3 is 3. And I'm just doing this in scratch work here because I don't have a lot of room. So then I get a negative 4 plus a negative 15 when I add those, which gives me negative 19/3. So my exponent here is going to be A to the negative 19/3, some really gross looking exponent. And then on the B's, you add those together, 2 plus 6 is 8, so I get B to the 8. And then the last step is I've got this negative exponent, so I need to take the reciprocal so that A to the negative 19/3 is now going to be a fraction. That's going to go at the bottom, and then the exponent is going to become positive. So this will give us B to the 8 over A to the positive 19/3. And if I wanted to do radicals or something like that, I could try to simplify that further, but we'll just leave it like that. And we end up with this. It's not pretty because we've got a fraction in our exponent, but that's simpler than what we started with. We're following the rules of exponents, and you know, it's very slow going. You want to make sure you multiply your exponents, simplify them, then you add them when needed, and there we go. Any questions? Okay. Well, that is rational expressions.